title of his talk is Towards an Understanding of 3D Newton-Cartan Geometry.
First screen is done. Sorry, which one is this one?
I think you just push the
okay. Thanks to organizers and to giving me the opportunity to present my work, and apologize for the colleagues also who have already heard my talk. I will also add some comments of some work on the progress, and I hope to give some new information about it. This is a work initiated with my PhD advisor Simon Ross, and some follow-up works with Niels Albers, Jelle Hartung, and Gabriel. So the motivation is holography is very powerful to help us understand the strongly coupled field theory, but we want to ask the question how general the idea of holography can be. Does the holography depends on specific model like ADS-CFT or relativity, or if I throw away some raw properties like relativity or something else, does holography still exist? And another motivation is how I initiated this project is puzzles, pathologies in the Lipschitz high spin theory. I will explain later. And in the second part of this talk, I will explain several examples of a Newton-Cartan Chern-Simons theory, and which can also first resolve the puzzles of Lipschitz high spin theory, and also provide the example of holography in the non-relativistic limit, which means it does not depend on relativity. And I will add some discussion at the end. So to understand the non-relativist, understand holography, it is very essential that we can understand what the symmetry group it has. Since for holography to work, for bulk gravity dual to the boundary field theory, we expect they have the same symmetry group. So for example, in the familiar ADS-CFT case, we have the isometry group to be SOD, 2, and in special case, for D equals to 2, we have the isometry can be split into the product of two copies of SL2. That's for each copy SL2, we can have the Chern-Simons theory taking values on it. And for example, how we can generalize the holography. Usually, for example, for SL2R, we have three places to generalize. First, we can generalize 2 to any integers or parameters, which gives us a higher spin theory. And second, we might generalize this real number field to p-adic number field, and which would be the p-adic ADS-CFT. And third, we might change slightly the name of the special linear to some other groups, which would be the third option, like take the non-relativistic of some parameters in the group to have a non-relativistic symmetry. This cube has been used widely to explain what kind of a theory we are considering. And we were in middle school, what we were taught Newton mechanics is we don't have relativity, we don't have quantum mechanics, we don't have gravitations, so we are just know F equals to ma. So after we turned on h bar from 0 to a finite value, we will have quantum mechanics, and when we reduce the the speed of light from infinity to a finite value, we are studying special relativity. And similarly, when we have finite g, we are studying the Newton gravity. And combining any two of these effects gives us new theories, such as the quantum field theory is a union of special relativity effect and quantum effects. And the general relativity is a union of gravitational effect and the special relativity effect. And both of these two theories has already been tested by experiment and observations to a very high accuracy. Our final goal is to try to understand quantum gravity theory with all h bar g and finite c. And one of the most famous results of the quantum gravity is the Hawking temperature. It depends on all these three constants. But very little attention has been paid to this corner, which is a combination of the quantum effects and the gravitational effects. This is indeed the effect of some kind of a quantum gravity, but without the relativity. And it is known as the Galilean quantum gravity. And so we would expect, just as with how we study general relativity and quantum field theory, by studying Galilean quantum gravity may give us some hint what a real quantum gravity could be. So we need to understand the Galilean quantum gravity, the non-relativistic limit. Let's first understand its symmetry group. One of the mostly used non-relativistic symmetry group is known as the Lifshitz symmetry. It is called non-relativist because time and space scale differently, parameterized by this dynamical exponent z bigger than 1. The gravity dual, which has this Lifshitz symmetry as its isometry, is known as the Lifshitz spacetime. And also there's a Schrödinger spacetime has larger symmetry group than Lifshitz symmetry. And especially at z equals to 2, there is an encasement of the Schrödinger symmetry group, and it contains the special conformal transformation. Sometimes it is called the non-relativistic conformal. One of the very fascinating work in 2012 was people find that both Lifshitz spacetime and the Schrödinger spacetime are vacuum solutions of the Chern-Simons theory, taking where the gauge field takes values in SLNR, so which means the Chern-Simons theory corresponds to the higher spin theory. And this is the Lifshitz metric, this is the Chern-Simons gauge fields, and this is the Schrödinger metric. But there's a pathology to this. Usually, when we have a Lifshitz spacetime, we are expecting it is not the vacuum solution of Einstein equation. Because we know the vacuum solution of Einstein equation is ADS spacetime, not Lifshitz. So to have Lifshitz spacetime as a solution in Einstein gravity, you would need some extra matter field to support it. And these matter fields, some by Shamika Chu, it was chosen to be massive gauge fields, and these components and the mass must be specific value, depends on the dynamic exponent z. But the pathology is, in Chern-Simons theory, the only matter field can support Lifshitz spacetime is the spin-3 matter. And the only non-trivial, non-vanishing component is the Tx squared component, which can be set to 0 if you choose the coefficients very carefully. These coefficients are the coefficients of the W2 and L1 generators. So if you, for example, if you choose all of them to be 1, this solution is still the vacuum solution of the Chern-Simons theory, but not the solution of Einstein gravity anymore. So the pathology is if I trust the equivalence between Chern-Simons theory and the Einstein gravity, then what's happening to Lifshitz solution? It is not the solution to Einstein gravity, but a solution to Chern-Simons. The resolution is, although in Chern-Simons theory, taking values, for example, in SL3R, frame-like fields have 24 degrees of freedom, which is 3 times 8. And the local Lorentz transformation fixed 8 of it, so the independent degrees of freedom, physical degrees of freedom, in this theory, from a Chern-Simons theory point of view, is 16, which exactly match the 6 metric component and the 10 spin-3 gauge field components. But for this map to be exactly one-to-one, there is a condition should be satisfied, which is a torsion-free condition. This condition is used to solve a spin connection uniquely from Weyerbein, because the Chern-Simons theory is a first-order formalism, but the Einstein gravity and spin-3 fields, these metric-like fields, are second order. So for this map to work, this condition must be satisfied, but for Lifshitz space-time, this is not satisfied, because except omega equals to a half a plus a bar, the two chiral parts of this Chern-Simons gauge field, there is 2 free parameters, so which means the spin connection cannot uniquely be fixed by solving the torsion-free condition. So we cannot trust this Lifshitz space-time interpretation. But if you check the for Schrödinger space-time in Chern-Simons theory, you will find that torsion-free condition can uniquely solve the spin connection. So which means you should expect the Schrödinger solution supported by spin-3 gauge field can solve Einstein equation with, of course, the spin-3 matter field to support it. These spin-3 matter fields just can be write down up to the quadratic order. And if you just take that into equation motion, you can check the equation can be solved to the perturbative order of this sigma. So I will move on to the Newton-Cartan gravity to clarify this problem further. Any questions so far?
Yeah, sorry. Very many questions. So I can think of quantum mechanics as 0 plus 1 dimensional quantum field. So it's quantum mechanics is number of spatial dimension is 0. So then turning on gravity, I could be trying to couple this quantum mechanics to gravity, and I thought that that's, so you can think of Feynman expansion quantum field theory is 1 dimensional quantum gravity. But this seems to be very different from what you have in mind. How do you think of what is a Galilean quantum gravity? What is supposed to be? You have this part of the cube where you start from quantum mechanics and goes up. I'm confused. What is a Galilean quantum gravity? How do you think about it? What is observable? So
Indeed, this lacks some intuition. So what I try to do is I want to find some of the third-party theory. For example, Chern-Simons theory tell me what kind of physical observables are. For example, holonomies, I can define something in Chern-Simons theory. And then, if I can build up a Galilean quantum gravity from the Chern-Simons theory, then I can try to ask what does that mean.
But you have a number of spatial dimensions, right? It's not like 0 plus 1.
No.
Yeah, it's also.
Okay. So why we need to think about the Newton-Cartan gravity from this? because the problem we had before is I try to embed, try to construct non-relativistic holography from a relativistic gravity. I want to embed something non-relativistic to a relativistic, so this is not really necessary. What's happening, how we study Einstein gravity is we just start from a relativistic symmetry group and build up a relativistic gravity. So why not just start from some non-relativistic symmetry group symmetry to build up a novel non-relativistic gravity so that maybe this problem can be resolved. And also, another thing is the Harshava-Lifshitz gravity, known as non-relativistic gravity, has the Lifshitz solution as a vacuum solution. And the dynamical version of Harshava-Lifshitz gravity is called, Harshava-Lifshitz gravity is the dynamical version of Newton-Cartan gravity. So I want to interpret the Lifshitz vacuum solution or find the Lifshitz solution by building up a non-relativistic Newton-Cartan gravity, and the Lifshitz solution must, spacetime must be solution of this theory. And based on some properties of Newton-Cartan gravity, we can classify them into 3 types. The first type is very similar to Einstein gravity. It's called torsionist or Newton-Cartan gravity. The tau is the time components, usually known as the clock frame. And in terms of Harshava-Lifshitz gravity, is called projectable Harshava-Lifshitz. And the second type is called the twistless torsional Newton-Cartan gravity. This condition usually implies d tau is somehow, there is a dynamic exponent z for any value. You just take this equation back, you see tau wedge tau is 0. So this equation would imply from a symmetry point of view, there exists a scaling generator, generates the scaling symmetry, such as H is Hamiltonian, so it satisfies some Lifshitz scaling. And the third type is torsional Newton-Cartan gravity, usually no constraints on tau at all. And one can find some similar example in Einstein gravity, which is like supergravity. You have some fermion fields, and there's no constraints on this tau at all. So we want to understand what kind of non-relativistic symmetry group we have here. The first one is the Galilean, and it has rotations. Let's just take 3D as example. It has rotations and has spatial translations, has Galilean boosts, and also a central generator N. Usually the central generator N is identified with non-relativistic mass, and because in relativistic theory, your energy and the mass, rest mass are related, but in the non-relativistic theory, they are different objects, so you need an extra generator to tell you that. And you can also introduce the cosmological constant, and this algebra together, this commutator together with this Galilean commutators will be called the Newton-Hooke algebra. And they are considered to be speed of light goes to infinity limit of a conformal group or any relativistic group. A Carolian algebra is usually something we take the speed of light goes to 0, and it is called ultra-relativistic limit. And Schrödinger algebra, Galilean algebra, together with the dilatation generator D. And at z equals to 2, Schrödinger algebra can have a special conformal symmetry enhancement, and the Hamiltonian dilatation and the special conformal symmetry transformation together form SL2 part. And there is an algebra called Galilean conformal algebra, And the special thing of it is it sometimes can be identified with BMS algebra in the special dimensions. So there are several ways to acquire non-relativistic gravity. One of it is I start from a non-relativistic symmetry group, gauging it, I write down whatever is invariant under non-relativistic gauge transformation. Second one would be write down high-dimensional Einstein gravity and do dimension reductions. And in this talk, I will use the first one. Try to start from a symmetry group and gauging it and write down whatever I can write down. So let me remind you how we did that in Einstein gravity. For example, in general dimensions for any Poincare algebra, I can take a gauge field taking values in this algebra. And I can also have a gauge transformations taking values in this. And to identify this gauge theory with Einstein gravity, we need to identify their gauge transformations of gauge theory to the diffeomorphisms of the general relativity. From here, we can derive the gauge transformations of Weyl-Bein. It depends on these parameters, eta and sigma. To identify it with the diffeomorphism of the B derivative, we need to make this term vanish. And to make this term vanish is the same as impose the torsion-free condition we just mentioned at the beginning. This helps us to solve spin connection uniquely from Weyl-Bein and also map the diffeomorphisms to the gauge symmetries. And by doing that, then you can write down the metric which is invariant under the local Lorentz transformation. So how can we do that beyond the Einstein gravity? Given the Bachmann algebra we just mentioned, we can write down a gauge field, take its value in it, and write down the covariant field strength tensor. But in general, in this theory, spin connection cannot be uniquely fixed by the Weyl-Bein. So the resolution in the work by Eric, he's not here, is I need the extra U1 gauge field. And so what I can solve is all of the spin connection in terms of not only the Weyl-Bein tau and the EA, but also in terms of extra gauge field. And similarly, by doing that, I can now identify the diffeomorphism with the gauge transformation of this Bachmann algebra. But the different thing is now the field invariant under the not the local Lorentz transformation, but the local Galilean transformation are clock field, clock Weyl-Bein, but with inverse spatial matrix. And if you write the mu down as the lower indices, it will not be invariant under the local Galilean transformation, just like your Einstein gravity, you build up something not invariant under the local Lorentz transformation, which is not acceptable. So the geometry field in this Bachmann gravity would be tau and the inverse spatial metric. But you can always define the Lorentz metric to be our familiar form. We will see that how this form will be related to the Lorentz manifold geometry later in an example. So after I understand how the gauge, how we can gauge algebra and map gauge theory to an Einstein gravity or a gravity theory, we want to write down the action rather than just play with the equation motion. To do that, we need to say, okay, is there anything can help us or to tell us how to write down the action? This is Chen-Simons theory. At least we can do that for 3D. In 4D higher dimensions, that would be hard. How did we do that in 3D? We just define Chen-Simons theory and takes a gauge field, takes takes value in this gauge symmetry algebra. But there is a trace here, must be a non-degenerate bilinear product defined on the algebra. In non-relativistic symmetry group, in general, this will be degenerate, so which means in that case this gravity theory will not exist. In this case, is flat 3D gravity. So in the work by Wheaton, he found that there is a bilinear product defined on this ISO 2,1 algebra, and he showed that this Chern-Simons theory is exactly equivalent to Einstein-Hilbert action. For non-semi-simple algebra, usually we will have degenerate invariant bilinear product. But sometimes, if we are lucky, there might exist non-degenerate bilinear product. So we need to solve this equation. What example given by Wheaton in his famous paper is I can start from an algebra called E2C, sometimes called 2D central extended Euclidean group. So there's a rotation here, and the commutator of the momentum part will has a central extension. And he find that by solving this equation, you can find a bilinear, non-degenerate bilinear product, which means you can define Chern-Simons theory or Weissman-Wheaton theory. This is something we want. So how can we define that for Bachmann algebra? For the Bachmann algebra we just mentioned, you can see just by using the Hamiltonian translation, boost the rotation and the central generator, the bilinear product is still degenerate. So to resolve that in this work by in 2009 is I need to introduce one more generator, S. And then I can have a non-degenerate bilinear product. This S is usually interpreted as the rest spin of a non-relativistic particle. And the Chern-Simons theory you can write down is this. And the extra generator S covers to a gauge field zeta. And zeta is, you can see from this action, plays the role of the Lagrange multipliers. By varying it, I'm imposing the condition d tau equals 0. This is exactly the torsionist condition of Newton-Cartan gravity. So which means the gauging Galilean algebra gives us a special type of Newton-Cartan gravity. It's torsionless. We can use the metric-like gauge field to write down what the action is. These two terms are dynamical terms. In Hrshav-Lipschitz gravity, there is the general parameter lambda here, because these two terms are respectively invariant under the local Galilean transformation. But lambda is set to be 1 here so that it is equivalent to Chern-Simons theory. And this phi here usually known as the Newton potential. So this is the general Hrshav-Lipschitz gravity, and the more general potentials may exist. But this is not enough to understand the Lipschitz holographic vacuum solution, because the Lipschitz vacuum solution has a scaling symmetry. So to do that, I need to gauge Schrödinger algebra. For z equals 2 Schrödinger algebra, if you try to add the symmetry generator S, you will find it will violate Jacobi identity. So to resolve this problem, to make the Jacobi identity satisfied and allow non-degenerate bilinear product, we find you need to introduce 3 more generators. And these red parts are the Schrödinger algebra, and blue parts are extra generators we are supposed to write down, and the black parts of this algebra are the commutators uniquely fixed by Jacobi identity. So by calculating the non-degenerate bilinear product of this algebra, you find there is a metric on it, which is parameterized by this number C1, and then you can write down the action. We call it Schrodinger gravity. And you can check that equals to Lifshitz gauge field solution is indeed the vacuum solution to this theory. This is a normal action interesting to us because, again, this lambda is fixed to be 1. But in general, for a conformal Harshad-Lifshitz gravity, this factor depends on the dimension. In 2+1 dimension, this factor is actually 1/2. So this is not any conformal Harshad-Lifshitz gravity we know. So it is new to us. And one can ask the question, what's the meaning of this extended symmetry? By writing it in terms of the Virasoro generators and some M generators, we find this algebra is nothing but a super Galilean conformal algebra with supersymmetry to be 1,1. Super is quoted in the sense which plays the role of supercharges is the commutator rather than anti-commutator. To identify this commutator to be with the anti-commutator, you need to take the linear combination of some anti-commutator of the n equals 1,1 super Galilean conformal algebra, and this epsilon 1, epsilon 2 must be Grassmannian valued, so that the commutator of y1 and y2, for example, will be proportional to epsilon 1 wedge epsilon 2, and the property of a Grassmannian value will transform this commutator to anti-commutator. It will give 0 minus some. Another example I want to show you is the Newton-Hooke gravity. I think this is more analogous to the ADS-CFT. We know in 3D SO, the isometry of ADS can be split into 2 copies of SL2. And if I want to make any analogy in Newton-Hooke, Newton-Cartan gravity in the non-relativistic limit, it's better I need to introduce the cosmological constant. So this Newton-Hooke gravity can be shown to be product of 2 copies of a P2C, known as 2D central extended Poincare algebra. Each copy of the P2C has 4 generators, and each copy also has non-degenerate bilinear product, parameterized by this gamma 2. So by doing the same thing, you can write this Newton-Hooke theory in the transilence form, and then you can write down the gravity part. The first part will be analogous to the Einstein gravity part. The second part will be analogous to the topological massive gravity part, and the third and the fourth part are just some kind of U1 generators introduced by this N generator and S generator. To see this analogy further, what you can do is just start from some Einstein gravity in 3D with 2 U1 gauge fields. And then you can write down the normal Einstein gravity and the topological massive gravity term with these 2 U1 gauge fields. And take the identification between relativistic gauge fields and non-relativistic gauge fields. The capital E, capital omega are the gauge fields, biobinds, and the spin connections of the Einstein gravity, and the tau and M are the spin connections and the biobinds of the Newton-Hooke gravity. And by sending alpha goes to infinity, you can show that the Einstein gravity will reduce to this Newton-Hooke gravity. And for each copy, you can realize that how the algebra can change. So this part, the L0s are the relativistic energy, and the curly Ls, zero curly Ns, are the non-relativistic parts. So this looks like energy equals to rest mass part, alpha identified with the speed of light, and the L0 is is like the kinematic terms in the non-relativistic limit. The vacuum solution can be written in the ADS form. This is exactly the ADS in global coordinates if you write down in terms of the Lorentz metric. But this part is not invariant under local Galilean transformation, so usually we don't write it in this form. The interesting part of this story is not only the supergravity, the vacuum solution part can be analogous to ADS-CFT, but actually you can impose similar Brown-Hanaud boundary conditions on the theory. So you can first use the Dirichlet, impose a Dirichlet boundary condition so that this part is fixed to be 1. And this gauge choice actually introduced the gauge transformation, and whatever your physical currents you introduce near the boundary must be invariant under this gauge transformation. So you can write down 2 possible physical currents in terms of this F0 and the Fn general physical currents. And by playing similar algebra as the Brown-Hanaud calculation, you will see it will transform like this. So this part will be Virasoro parts. And there's a central term, and this part will be the U1 affine parts. So in terms of Fourier modes, the asymptotic symmetry algebra is a Virasoro affine U1 for any finite alpha. By sending alpha goes to infinity, we got a novel Virasoro algebra known as twisty warped Virasoro. For any finite alpha here, you can actually remove the second commutator by redefinition of Virasoro generator F. But in the alpha goes to infinity limit, you cannot do that. So this is the table I want to claim the novel holographic can be analogous to the ADS-CFT holography in many aspects. For example, the split of isometry group, the Courcide construction of bulk, and the Virasoro asymptotic symmetries, and the study of Wasserman-Witten models, and the possible extension to the higher dimensions. But there are also some, such as BTC black hole analog, higher spin generalizations, entanglement entropy in terms of geodesics, are still not clear to us what that means. How much time do I have?
About 10 minutes.
Okay, then I have some time say a few words about the work on progress. So all of these derivations so far are just focusing on supergravity level. So next question we are working on is how can we understand that at the string level? How to study a string propagates on the curved manifold like this Newton-Cartan gravity. So what we do is to follow the work of Kutasov and Seiberg and Gibbon. What they did is, your study a string propagates in the ADS space-time with NS2 form, and you can write down the currents of SL2R in terms of the Wakimoto representation in the beta and in terms of beta and the gamma free fields, and by integrating over all these string fields on the string worksheet, you can acquire space-time Virasoro algebra, and your central charge in Brown-Hanaud central charge is actually proportional to the winding number of the worksheet long string. All this can be done in this P2C Newton-Cartan gravity, and we have already done that, and also the central charge in our case can be acquired similarly in the long string interpretation. And one more thing is you can actually derive the Wakimoto representation of P2C from a non-relativistic limit of Wakimoto representation of SL2R plus U1. what does this mean for string theory is we have two extra U1 gauge field. I prefer, if I want to embed the theory into a string theory, I can identify this U1 as the R symmetry of the, for example, supergravity. So which means I can define a string coupling proportional to this alpha minus 2, to the minus 2. So energy will be dilatation times this string coupling, and similarly also similarly the U1 charges. So alpha goes to infinity limit. At that limit is like E equals to J. So which means that's a BPS limit. So by zooming in, by sending alpha goes to infinity, we are actually zooming in the lowest lying states in the spectrum. So which means it is expected this kind of a normal non-relativistic holography should appear in the near BPS limit of some supergravity, such as in our case, this is n equals to 2, 2 is enough. But you can try also ADS3 times S3 times T4. Zooming in this limit, you should have an effective description in terms of its normal non-relativistic holography. And one more thing is, this holography is simpler because it is a foliation in the holographic direction. So which means when we are going to reconstruct the bulk gravity, we don't need to reconstruct the whole space-time. But instead, we just need to reconstruct the foliation of the space-time, which sounds like simpler, maybe a minimal setup of bulk reconstruction. And from this table, I want to say is, usually ADS safety is relativistic bulk gravity with the boundary to be relativistic field theory. And the work of Chemicatru used the massive gauge field to support the gravity. Lifshitz gravity is relativistic gravity in the bulk, but non-relativistic field theory in the boundary. Newton-Cartan gravity is non-relativistic in both cases, but our example looks like non-relativistic in the bulk and the relativistic field theory at the boundary because that's a foliation of the boundary space-time. So what we have discussed that we give an interpretation of Z equals 2 Lifshitz solution in Chern-Simons theory in terms of this Newton-Cartan gravity. We show instead you should not think about higher spin theory, but the Newton-Cartan gravity for that. But this only explains Z equals to 2. Actually, that Lifshitz solution for any dynamical exponent, integer dynamical exponent Z exists in Chern-Simons theory, but our approach can only explain Z equals to 2. So it's better if we can have an explanation of general Z. And so at the end, for future works, except the Wakamoto representation of string theory in this non-relativistic background, I think pretty much you can do everything you have done in ADS 372. Okay, thank you.
Any questions for Jan?
So maybe about your BTZ black hole analog. I mean, what's exactly the problem? Is it solving the equations of motion that's the problem, or is it something in the holonomy representations of BTZ?
Holonomy representations.
But so that you're saying that doesn't work, or you just haven't tried it yet? Or?
We actually take the gauge fields, and the gauge field is you can write down a BTZ black hole gauge field, and you can define holonomy. And we take that limit, we got something. It looks nothing special from gravity side. We just don't quite understand it. We don't have the horizons, so we don't quite understand. But the reason I think behind it is usually when you think about a black hole, it's from Newton's perspective, it's something light cannot even escape. But now in the non-relativistic limit, your static speed of light goes to infinity. So which means in principle light can escape anything. So why do you have black hole? So I think that's also a very weird problem.
But I mean, it's somehow similar to the higher spin story where
Yeah.
somehow even the singularity is not really important, right? Because you can gauge it away with higher spin transformation.
Yeah, yeah. I think you can impose holonomy conditions
Yeah.
to define something.
So holonomy is probably the way to go, like
Yeah.
the higher spin.
Yeah, that's why we want to build up everything in terms of consign theory. It's well understood. We have a third party to help us understand what could be defined.
Okay, let's thank Yang again. Lunch is downstairs, bottom floor.